The broadcast is now starting. All attendees are in listen-only mode.
Well, hello everyone and welcome to the latest iFormulate Introduces webinar. Today we'll be taking a look at the topic of fluid bed processing. We're pleased to be running today's webinar in association with the University of Leeds. At the end of this webinar, we'll tell you more about a new course in January 2019 where you'll be able to learn more about the subject. My name is Jim Bullock from iFormulate, and I'm joined today by Professor David York from the University of Leeds. Since 2012, David has been Chair of Structured Particulate Products in the Department of Chemical Engineering at the University and has previously held senior roles in process development and product development at Procter & Gamble. This webinar is designed as an introduction into the basics underpinning the process, as well as the implications for design, operation and uses. This webinar is being recorded and will be made available to you. It will last about 40 minutes. At the end of the 40 minutes, you'll be able to ask questions using the question function in GoToWebinar. And tomorrow, after the end of the webinar, you'll get an email which will provide you with access to a recording of this webinar and a PDF of the slides. So I'll be covering the introduction and the section entitled Why Choose Fluid Bed Technology. David will then look at the subject in more detail in sections 2 to 7, and I'll finish off by telling you how you can learn a bit more. Just a quick overview, a little bit about iFormulate, in case you don't know us. We're a company founded by David Calvert and myself, and between us we now have around 60 years experience working in the formulating industries. We've been in business for just over 6 years now, and we bring our own experiences and knowledge gained across many industries and in various functional roles. And by combining those experiences with the expertise of a number of associate partners, we're able to assist our clients effectively with a number of different assignments. We divide our activities in 3 business areas. The main area predominantly is in consulting, where we carry out innovation and technology consulting, mainly in formulation technology for client companies in industry. As part of iFormulate strategically, we've carried out and assisted strategic projects for sector bodies and associations in the area of formulation, such as the UK's Knowledge Transfer Network, the UK's National Formulation Centre and the Royal Society of Chemistry. Under iFormulate Skills, we design, deliver and promote training courses and programmes in formulation science and technology, which may appear under our own banner or may be in partnership with third parties. And this webinar is part of iFormulate Skills activities. So today's an introduction, and we'll start by asking why choose fluid beds at all. It's a short presentation today, so we can't cover everything about fluid beds. Let's just go back one step and just focus on drying as an application. Why might you want to dry products? Well, first of all, you usually do drying at the end of a production process, so it's a final step in production. It usually involves the removal of a solvent, often water. Drying is done to reduce transportation costs by removing bulk from your product. It can make materials much more suitable for handling. It avoids moisture that can lead to corrosion in storage or in use. And dry products can be mixed later on in a subsequent formulation step in solution or slurry to make consistent products, and dry products are less likely to become contaminated by microorganisms, so drying can increase the shelf life of products. So that's why you want to dry products. But of course, you've normally got other objectives than simply drying your product. I often say drying your product is almost certainly not the only thing you're trying to do with it. So what other things might you want from your drying process? You don't want to harm your materials. You may have sensitive active ingredients in there, for instance, sensitive to heat or to other environmental factors. You'll want good yield and economics. You want a product probably that flows well, or a product that isn't dusty. You want particles that may redisperse well in subsequent application. You may want, for instance, particles that can be compressed in a tablet press if you're making tablets. You may want to produce a product with a defined particle size, fine particles or large particles. Those particles might be might have to have a defined strength, strong or weak. In short, you might want engineered particles, and that's a phrase that sometimes we use, and people often say to us, well, what do you mean by engineered particles? So here's a slide that kind of summarizes what particle engineering is. It's really about understanding the sorts of particles you want to make, and then understanding how to make them, and then making sure that you've made those particles. Because the particle structure influences the physical properties of the final product, those properties such as flow, dust, redispersion, porosity, controlled release, and so on. So you can give the final product the properties you want by controlling particle size and distribution, the shape or morphology of the particles, the mechanical strength of those particles, whether they can redisperse, whether they're mechanically stable or friable. And you can also control the internal structure of those particles and encapsulate them to give them some sort of protection or controlled release properties. So that's particle engineering, and those are the reasons you might want to do it. So let's move on to drying and the sorts of choices of drying that you've got. And I went to a website called Solids Forum to find out really how many sorts of drying technologies there are. And there are a lot here. There are about 190 types, which shows how creative engineers can be in this industry. So you've got a huge amount of choice here. Unfortunately, we won't be going through all of those today. We don't have time. So let's just look at a few of the more common types. And here we've summarized some of the more common types with advantages and disadvantages. You might need to classify your material in terms of how fluid it is, whether it's wet, whether it's a paste, whether it's a slurry or a solution. Just going to run through just not all of these, just some of these. So tray or shelf drying can lead to very low losses. It's very versatile. It's very good for small batches. It gives you pretty uniform heating of the material, but it's slow to manually unload and load those trays, and it gives you little opportunity for the particle engineering we talked about. Freeze drying is often used for very heat sensitive materials. It gives you a nice porous redispersible product, but it's slow, pretty complex, and expensive. And there's limited opportunity for particle engineering. Microwave drying is often also used for heat sensitive materials. It's very good for bulk materials and viscous materials. It's pretty rapid. But of course, once you move to larger batch sizes, then it's difficult for the microwaves to penetrate, so it's less suitable. And there's little opportunity again for particle engineering. And spray drying, which we talked about in previous webinars, is rapid. It gives you good heat and mass transfer, and it can give you particle engineering. But it can be very complex and capital intensive, so it's quite expensive, or it can be. And you have to be able to start with a liquid feed that you can pump through the spray nozzle. So this is disadvantages and advantages for all sorts. Let's move on to fluid bed as a drying process. When in fact this covers not just drying but other applications of fluid bed processing. So not just drying but also chemical processing like synthesis, cracking, combustion, incineration. Drying not only of chemicals but of really quite large particles like cereal grains in foods. Also cooking and freezing processes can be carried out in fluid bed processes as well. Granulation, so making particles bigger by agglomerating them, that's often used for things like pharmaceuticals, where you want to make compressible granules for tableting, where you want to make water dispersible granules for agrochemicals, or whether you want to make free-flowing detergent granules. And you can also engineer and coat particles, encapsulate and coat them. So things like probiotics in foods, agrochemicals again, where you might want to encapsulate an active ingredient, or pharmaceuticals where you might want to do the same. So a huge variety of applications in fluid bed processing. And the advantages, again, you've got a good surface area in fluid bed processing. David's going to talk to you a little bit more about that in a moment. That gives you good contact in the fluid bed, high mass transfer, high heat transfer, leading to a uniform product. It can be operated in batch or continuous processing. You can use it with care with heat sensitive materials. You can engineer those particles to disperse and flow well in the application. You can create, for instance, granules, and you can encapsulate and coat them. You do, however, need to be able to fluidize the input material, and that's something that David will certainly concentrate on in a moment. So in general, particles need to be 250 microns in size or larger. There is a risk of particle breakdown or attrition, which can create dust. You have to maintain high pressure drops in the fluid bed, so there's potentially high energy consumption, and fluid beds can be less suitable sometimes for flammable or toxic material. So at this point, to take you through a few more details about fluid bed processing, I'm going to unmute David and hand over to David for the next sections.
Thanks, Jim. The next slide shows the basic concepts of how a fluidized bed operates, and it's basically fairly simple to understand. The joy of fluid bed processing comes with the complexities that occur because of what you do and what you use inside the bed. Basically, you start off with a container with a perforated plate at the bottom, and ideally the perforated plate is smaller holes than the particles. The particles are then lumped on top of the plate, and you've got a classic then static bed, a packed bed. Only compared to standard packed beds, these particles are much smaller, and one of the advantages of that is they have a much higher surface area for doing what you want to do at the surface. And since most interactions, heat transfer, chemical reactions take place at the surface, there's a great advantage of having very fine particles. But at this stage on the left, those particles aren't, that surface area is not accessible because it exists as a lump held down by the weight of the particles due to gravity. What then happens is you pass air through the bed from the bottom. You force air through, and as it goes around the particles, there's resistance to the airflow, and that creates a pressure drop. As you increase the airflow, that pressure drop becomes equal to the pressure drop caused by the height and the density of the particles. And at that stage, the particles start to be able to move around relative to each other, and you get the onset of fluidization. And a little bit more air, and you've created a fully fluidized bed. Try to show that in a diagram on the right-hand side. These particles now are moving in a very random structure, left, right, up and down, side by side, side to side, and acting like particles or molecules within a liquid. So to all intents and purposes, they have a surface, they have a density. If you put something on top of them, they'll sink just like a liquid. So the critical bit then is to get the flow rate such that you get the pressure drop to equalize the pressure caused by the weight of the particles. And if you increase the flow of the air through the bottom, what you do is you make for more motion of the particles, but you don't get much more benefit from it because you've already fluidized the particles. In the next slide then, the properties of the fluid bed, again, are a bit like a liquid. So it has a defined pressure, and the particles can move in any way that you want. And it has a bubbling surface, just like you're boiling a pan of water. The air comes up through and bubbles. One of the things you can do with the size of the distributor is by controlling this hole size, you can control the size of the bubbles, and that can be very important depending on the application. So you've now got lots of fine particles with a huge surface area moving around randomly. And consequently, you have an awful lot of mixing that's occurring in there, mixing between particles and mixing between the particles and the air. And that gives you a huge increase in mass transfer. And mass transfer in this sort of system is also very good for heat transfer. And mass transfer is also very good for any chemical reactions that you want to influence in this system. So that's the properties of the fluidized bed. There are some simple equations, or there are lots of equations actually. I've picked one of the simplest to describe the key factors that influence whether a bed is going to be fluidized or not. And UMF is the minimum fluidization velocity, and it's really dependent upon gravity, which normally we can't control, the particle size squared, the density difference between the gas or the particle and the gas, or even a liquid. You can use these with liquids as well as the fluid, divided by the viscosity, and there's a factor in there that depends upon the shape of the particles. So spherical particles fluidize much easier, and there's a voidage term that comes in there. But the thing I want you to grasp really is the minimum fluidization velocity is critical upon the density of the particle and the size of the particle squared. That's the critical aspect. The consequences of that are shown in the next slide. The particles then are fluidized, and they can be blown up into the air above the bed surface. As you increase the velocity, you don't improve the fluidization, but you can get to a stage where the velocity is so high that you can actually fluidize the bed and blow the particles out of the bed. So typically with a normal product that goes into a fluidized bed, you have a range of sizes within the particles that you put in. And it's critical that you use enough air velocity to fluidize the largest particles, which means you've got excess velocity for the smaller particles. And if you get to a situation where that velocity is high enough, you can reach the terminal velocity of the particles, as shown by this simple equation here. And at that stage, you can actually blow the small particles out of the fluidized bed. Now, that's why fluidized beds will always come with cyclones and filters in them to trap any material that gets taken out of the bed. You can use this to your advantage, though. If you carefully design that velocity, you can use it as a way of sieving off fine particles from a wide distribution of feedstock going in. It's a very efficient way of screening out fine particles. Again, it's dependent upon the shape of the particles, so that range between the terminal velocity and the minimum fluidization velocity can range from about 9 to 1 to 90 to 1, depending on the properties of the particles. On the next slide, the consequence then is that different particles will need different air velocities. As I said, you can segregate particles, and in the extreme, you can use that segregation to blow stuff out. Particles that have different densities and sizes, then, if you haven't got enough velocity in the bed, will actually tend to segregate and give you bigger particles on the top and smaller particles on the bottom. So you need to ensure sufficient velocity to fluidize the whole product. Next slide. So what can you use it for? Well, the high mass transfer and high heat transfer can be used in a number of, and are used in a number of instances. So you can use the beds for very efficient heterogeneous reactions. So coal-fired power stations will pulverize the coal feedstock going into their furnace, and the furnace will actually be a fluidized bed. So you get maximum heat transfer and mass transfer in there, and have a very high rate of burning in the power stations to generate the heat. That consumes the particles, but if you don't want to consume the particles can actually be catalysts. So you can have a heterogeneous reaction on the surface of the catalyst, gain the advantages you've got because of the fine particle size. You've got a very high surface area and a very efficient way for catalytic reactors, commonly used in petroleum, hydrocarbon cracking. So many instances where you can use these to react solids and gases together. Another way is area is drying. Again, your advantage is you've got a very high surface area, and that helps you dry much faster. The second is that you've got, unlike a lot of drying processes, you've got the ability to have a long residence time, and consequently you can dry at lower temperatures, particularly for temperature sensitive materials. And often you see instances where the fluidized bed is an extra capacity at the exit from a spray drying bed tower, in order to increase either capacity or allow you to get the last amount of few percent of solvent out of your spray dry products, but at a lower temperature and not damage thermally sensitive materials. Again, often fluidized beds are used to cool products, take them down to temperatures where they're much crisper and easier to operate. And often when you've got a fluidized bed dryer, you will have a fluidized bed cooler tacked on to the downstream end. Because of the mass transfer within the bed, the randomness of the particles moving around, and those particles turning and spinning within the bed itself, fluidized beds are very good for coating. Here you spray a liquid containing a polymeric solution onto the surface, and as the particles come to the surface and turn around, they get hit by the liquid, and over time they get hit in lots of different places, and you can form a nice coating around the particles, and that's used a lot in encapsulation. Finally, the particles, if the coating solution is sufficiently viscous and the drying is sufficiently slow, you can build up the liquid onto the surface of the particles, which become sticky, and those sticky particles stick to each other, hopefully in a controlled manner, and you can start to then agglomerate the fine particles into larger particles. This is a very different way of agglomerating compared to high shear agglomeration, because of the way the particles tack together at the surface. You get a very low density particle with a very high porosity, rather like a raspberry structure. And they're used where you want to have low bulk density or very high dissolution rates. So it's a common way of what they call instantizing food, such as powdered coffee and milk powders, where the intent is to allow you to increase the particle size so that these soluble materials can get a chance to disperse quickly as the consumer uses them. So lots of different things that you can do with fluidized beds, and you can combine them as well. So it's a very flexible process with lots of opportunities. Now, things aren't necessarily as simple as we'd always like them to be in nature, and that goes with fluidized beds. Here's a chart that talks about different classifications of powders, and it's based on the work done by Geldart quite a few years ago, a very influential paper. And on the left-hand side, you've got the density difference between the particle and the fluid, and on the bottom, you've got the diameter of the particle. And there's 4 different zones which speak to how easy it is for the powders to be fluidized. So the ideal zone is zone A. Those are very easy to fluidize, and consequently, that's the one that most people operating these processes strive to get their particles. And you can do that by controlling the diameter of the particle to a large extent. With your particles, it's very difficult to change the actual density of the particles, but you do have some capability of changing the feedstock particle size. smaller than that size, the particles are very, as you can see, very small, tend to be lower density, and they are very difficult to fluidize because you've got another factor that's influencing the system, and that's cohesion. Particles that are very fine tend to want to stick together, to lump together, thanks to van der Waals attractive forces, but also if you've got some cohesive nature of the surface as well. These require an awful lot more force to get them to separate out. And then you've got the B and the D type. Again, you're going up in particle size. Remember, the velocity you need goes up with d squared, and also the density tends to be going up as well. And so the beds become harder to fluidize until you get to the group D, where you need such high velocities of air that you've got what's called a spoutable bed. So you're basically blowing these particles with a considerable velocity out of the surface of the bed, a bit like the corona on the sun, blowing out into space. So these are much harder to control, although we'll come across an example later on where spoutable beds can be used to our benefit. On the next slide, there are, as with everything in engineering, lots of different designs, but they can be simplified into batch designs, continuous designs, and spouted. We'll talk about those briefly. And then there's two ways of operating them, either static beds or vibrating beds. A vibrating bed is where you've got some mechanical vibrators attached to the bed, and they shake the bed at a reasonably high frequency. And these are used when you've got slightly cohesive sticky particles and you're using the shock force of the vibration to allow you to get easier fluidization. They tend only to be used if you have to. Static is a much simpler way of operating them. On the next slide. So continuous bed, very simple. Again, you've got an elongated bed here. The feed comes in on the left-hand side, falls into the bed. The bed then moves around. The particles, sorry, in the bed moves around, and because you've got a height difference between the feed and the exit, and because you've got a fluid type behavior, then the particles move from the left, go along over the air, fluidized, and then come out at the back through the outlet. And you can control the height or depth of the bed by having a weir that you can control. And this can control then the residence time within the bed. Important to note that not every particle in this system will have the same residence time, because of the random movement of the particles. You'll have a residence time in the bed. You can add internal weirs into the bed to give you a lot more control on the residence time and the residence time distribution. So that's another optimization that you can do with these beds. They tend to be used for very high throughputs because of the simplicity of the design and because it's a continuous process. Next. Here's an example of the spouted bed, and the classic spouted bed most people know as the Wurster. And here you've got a schematic of the Wurster coater, and you can see that it's a fluidized bed, but it's fluidized in two ways. It has two types of fluidization. The highest velocity is at the center, and that pushes particles very quickly up vertically inside a cylinder. And when they get to the top, they come out of the cylinder, and the air coming round the annulus is nowhere near as high in velocity, and the particles fall down and fluidize. But since they're still fluidized, they move back into the center. And what tends to happen here then is these particles circulate. It's a forced circulation bed many thousands of times in a batch process. And if you are spraying on a liquid at the bottom, you can coat the particles very, very efficiently. So these have been used and are used to provide a very efficient way of providing a consistent quality coat. And on the top left, you've got a picture of a particle which we've coated. It's an inorganic particle and is being coated. You can see it's a cutaway, and hopefully you can see with the arrows the thickness of the coating. Typically, to get a good consistent coating, you need about 15% by weight of whatever you're coating with as a solid to make up for any deficiencies in the particle sphericity. Obviously, more spherical particles are easier to coat. And at the bottom there, you've got a nice little picture of one of my raspberries from the garden, but it shows you how the different particles are tacked on together. So this is an example of a spouted bed where you're deliberately forcing stuff up at high velocity through the center. And there are designs now that don't have that cylinder. But here's one we've made for the course. It's deliberately made in acrylic so that people can see it. And I don't know if you can see quite as easily, we've got some particles blowing up the middle and also some particles coming down the side. We've colored them green so it's much easier to see. So this is something that people will get a chance to see and to play around with in one of the many demonstrator examples we've got for the course. Next slide. So in summary, these fluidized beds are very versatile. They have lots of different functions, and you can design them in many different ways to optimize the function that you're trying to operate. The behavior depends an awful lot on the particle properties. So particle density and particle size are the two critical ones, but also particle shape can have an influence. So I've tried to give you an introduction into the basic concept to help you appreciate what you can do with these. Obviously, we haven't been able to go into a lot of other important factors. So we haven't been able to cover the challenge of fragile particles. Obviously, these are particles are hitting each other to fairly high frequency, so you can generate dust. Particle shape is a critical factor in how these behave. It's possible, if you get the wrong conditions, to make these beds up. So instead of sticking particles to themselves, they can stick to the bed, or they can grow into large particles that won't come out the exit. So that's a challenge. The design of the plate through which the air is forced is also important, and that we'll cover in the course in a lot more detail. But you can imagine that the tinier the particle, the tinier the holes, the better the smaller the air coming through, but that increases the velocity. So there's a number of considerations to be taken into account. How you start up and shut down these beds is also important if you want to have a smooth, continuous operation, and that goes for a lot of powder processes. And developing strategies to cope with very different materials. The Geldart chart's helpful, but it's not the final word in this area. There are lots of ways of coping with cohesive materials, very fine materials. So Jim mentioned 250 as a minimum. There are ways of operating well into the hundreds if you design the process right. So that's a summary of fluidized beds and how they operate.
Thank you very much, David. And in a moment, we'll be taking some questions for you. And for that, you can start using the question function box in GoToWebinar. So just wanted to cover a little bit more detail about that course that we've mentioned. That will take place in Leeds at the university between 16th and 18th of January next year. We provided a link for you there. Registration is now open. On day one, just to summarize again the sorts of things we'll be covering, we'll be doing the basics in day one, and that's what causes powder beds to fluidize, those properties of powders, what things you need to look out for, the watch outs, starting to introduce the topic of particle engineering, and there'll be a raft of practical demonstrations in groups during that day as well in the lab. Day 2 will move on to industry case studies, thinking about the importance of the bed design and how that operates, operating parameters, startup and steady state operation, those real life case studies from a number of different industries, and carrying on with the practical group demonstrations in the lab. And on the final day, there will be really covering new developments and innovations. So the latest developments from both industry and academia. There will be a problem-solving forum. And I should say that, like all of the courses run by the university, these are highly interactive. We've got a number of different lecturers from industry and from academics, and there's a really good chance during those 3 days to interact and to ask them individually all sorts of questions that you might want to know the answers to. So we hope to see a good response for that 16th to 18th of January next year. So what we're now going to do is open up for questions. You're remaining muted as attendees. So please use those chat boxes or the question box in particular. If you have any follow-up questions, please email us at info@iformulate.biz. We'll send you details of how to access the recording of this webinar tomorrow, and any other training that we do you can find on our website with that web link there. So just looking to see if we have any questions today. I can't see any. So we're going to give you one last chance to ask any questions you may have. No, I don't see any. So thank you once again, David, and thank you everybody for attending today. And we look forward to hearing more from you and seeing you at further webinars or indeed in Leeds. Thank you very much and goodbye.